In this lesson, we are going to talk about parametric equations. So let's look at an example first. A rock is dropped from a 420-foot tower. It is modeled by the equation y equals negative 16t squared plus 420. Okay, so we've got two variables. We've got a y and a t. The y, if we think about as the height of the rock, and t is time, well, this is fine, but this doesn't tell us anything about height. It doesn't tell us anything about the like a horizontal distance. So we can superimpose this parabola onto another curve in parametric mode. For example, suppose the rock falls in the vertical line x equals 5. So we know what that looks like. Vertical line x equals 5 is straight up and down. Okay, so that would be our horizontal, our x horizontal. So if it goes straight down, the horizontal doesn't change. It would stay at, in this case, 5. So now we've got an equation to represent the horizontal, an equation to represent the vertical. We can put these together for our parametric equation. So we're going to start off by using our calculator to graph this. So pull out your calculator and, uh-oh, mine's broke. Let me fix it. All right, back with a fixed calculator. So the first thing you want to do is change your mode to parametric. So you're going to push mode, you're going to cursor down until you get to func, and we're going to cursor over to parametric. So we're used to graphing in our function mode where we've got a y and an x, and a y and an x axis. We've used the sequence mode back when we did sequences in series. We haven't yet used PAR, which is our parametric mode. So now make sure parametric is highlighted, and now go to y equals. And note the difference. We don't have just y1s anymore. We've got x1 sub t, y1 sub t, x2 sub t, y2 sub t, and so on. So each of our functions have a pair of equations, one for x and one for y. Okay, so this is what we're going to see as typical for parametric equations. Let's graph this one. X equals 5, so we're going to put in x equals 5. Y equals negative 16. And now when you put the variable button, the xt theta n button, it's going to come up as a t instead of an x. Square that, and we're going to add 420 to that. Seems like that's the height of our, yep, sure is height of our tower. Now we're going to graph it. Before we graph it, let us set our window. Okay, so we're going to set our window to, well, let's look at our table first. I'm a graphing person, so I have a tendency to go to graph first, but let's go to our table. So, second table. Okay, so if we're at t equals 0, notice we've got these two columns here. We've got 5s all the way down for our x's, so let's fill those in. 5, 5, 5, 5, 5, 5. Okay, because x equals 5, it doesn't matter what t is, x is always going to equal 5. Now if we go back to our y column, we've got 420, 404, for t equals 1, 356. 276, 164, and 20. So just pulling these values straight off of the table in our calculator after we've put in our parametric equation. Okay, so this is kind of neat because it tells you at these different time values, what is our horizontal, stays the same, and then what is our vertical. So this will be even more interesting if the horizontal changed, but it didn't. Okay, to view this graphically, set your window to these values. All right, so we're going to go to window. Notice we've got a little bit different window arguments here. So Tmin is 0, Tmax, we're going to make that 5. T-step, we want to step every 1 second. So remember time, t's, and seconds. X-min, let's make that 0. X max is 10. X scale is already set at 1. We don't mess with that. Y min is 0, and Y max boosts that up to 500. All right, so now let's graph it and let's see what we get. Okay. Get a good old horizontal line. So thinking about what we should expect, this is the path of our rock. We've got our X is our actual horizontal X. Y is the height. So even though our Y equation was quadratic and was parabolic, this represents the height. It's even clearer when we press trace. Okay, so when we press trace, we've got all kinds of things going on here. We've got both our X and our Y part of our parametric equation. And we've got our point here, which is at time 0, X equals 5 and Y equals 420. So it gives us all that information, and if we cursor through, then it tells us where our rock is at each second. Okay, kind of neat. All right, so let's look at another example. This says graph X equals t squared minus 2 and Y equals 3t for the given parameter intervals. Okay, number 1 for t between and including -3 and +1. So let's do that. Let's make a table first before we graph it. Okay, I've got a table here. I'm going to put my t values first. T values first. That's beautiful. And then my X values and my Y values. Okay, I want to make a 3-column table. I'm going to bold these a little bit. Okay, and then let's fill in what we know. Well, we know we want to go from -3 to 1, so let's go -3, -2, -1, 0 to 1. Okay, so now we want to fill in our X's and Y's. So we're just going to plug each of these into our X equation and into our Y equation. So -3 squared is 9, take away 2 is 7. We could plug this into our calculator again and go to our table, but it's just as easy to plug these in. -3 times 3 is -9. -2 squared is 4, take away 2. -2 times 3 is -6. -1 squared is 1, minus 2 is -1. Get -3. 0 minus 2 is -2. 0 times anything is 0. 1 squared minus 1 is -1. 1 times anything is itself. Okay, so there's our table for t values between -3 and 1. So if we graph those, okay, going down to our graph, we're going to have the same type of a coordinate plane where we've got X on our horizontal axis, Y on our vertical axis. Okay, and we're just going to plot those points. So let's start off at time is -3. And we're going to do 7, -9. So 1, 2, 3, 4, 5, 6, 7. Down 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. -9 is way at the bottom. Okay, so we're going to plot a point there. And I'm just going to label that t equals -3. Okay, going on to our next point, 2, -6. So 2, 1, 2, 3, 4, 5, 6. Okay, there's our point at t equals -2. And at -1, we get -1, -3. And so on. -2, 0. At time equals 0. And at time equals 1, we have -1, 3. Okay, so we can see the pattern in this. It definitely looks like a parabola that's opening to the right. It looks like if we were to continue on with our t in the positive direction, that it would curve back this way and be symmetrical about the x-axis. Let's see. The next two ask us to graph it up to 3 as our upper limit, and then they change the lower limit. Well, we're not going to change the lower limit. We'll just change the upper limit. So let's go out to 2 and 3. So 2 squared is 4, minus 2 is 2. 2 times 3 is 6. 3 squared is 9, minus 2 is 7. 3 times 3 is 9. So we've got 2 more points, 2, 6, and 7, 9. 2, 6. 1, 2, 3, 4, 5. Oop, that should be up 1. That's it, time equals 2. And 7, 9. So over 7, let's go up a little bit. 7, 8, 9. 7, 9. Okay, so if we were to graph from -3 to +3, and you can see how we could fill in between with a curve. It's not just these singular points. We would get a nice parabola opening to the right that would be of the form y equals, nope, scratch that, x equals y squared. Okay, with maybe a shift to the left and a vertical stretch. All right, so let's say that we want to convert from parametric form to our function form, our standard function form. Example, algebraically eliminate the parameters for the example above. The equations are x equals t squared minus 2 and y equals 3t. So we're going to find the equation of that parabola. And step number 1 to do so is to look at the graph. Okay, anytime we're asked to get rid of the parameter or to find this in function mode, first step we want to do, look at the graph. All right, we've already graphed it. We know it looks like a parabola opening to the right, and we know we should expect our equation to be of the form x equals y squared with some transformations going on. Okay, step number 2. We want to solve for t. So let's take our x equation, x equals t squared minus 2, and we're going to solve it for t. So add 2 to both sides, square root both sides, and we get t equals, don't forget the plus or minus, square root of x plus 2. Okay, once we find t, step number 3 is we want to substitute. Okay, we want to take this t now and substitute it into our other equation from our parametric form. Okay, so y equals 3t, and now we're going to replace that t with what we just found t to be equivalent to. Okay, bam. So we've got an equation here. We don't have any more t, but we got to solve so that it looks like our standard form for a parabola, because we know that's what we should expect it to look like. And we can't have this plus minus in our function. Okay, so to get it to look like that, we know our y is going to be squared. We know we got to get rid of this radical. So let's go ahead and square both sides. Okay, square both sides of the equation. It's going to do a couple of good things for us. It's going to give us y squared on the left. It's going to give us 9, and then that's going to get rid of this plus minus, because whether it's a plus times a plus or a minus times a minus, either way we're going to get x plus 2. Okay, so I want to get this x by itself, so I'm going to distribute my 9. Okay, do my algebra, subtract 18, divide by 9, then I get x equals 1/9. Oops. y squared minus 2. Okay, so there's my equation. It's in our standard form for our conic section of the parabola, and we eliminated the parameter t. Okay, and this matches with our graph. We've got a parabola opening to the right, shifted to the right 2, and a vertical stretch by a factor of 9. Okay, so here's another quick example. I would like for you guys to do in your notes. Remember, don't forget step 1 especially. Make sure you look at the graph, put that in your calculator. Graph it, it's going to help you find the equation. If you can find the equation just from the graph, then do so that way. Okay, let's say we want to go from a graph or from a couple of given points to a parametric equation. How are we going to do that? So we're going to use vectors. Okay, since this unit started off being about vectors, and it's going to end up being about vectors. So number 1, example, we're going to find the parametrization of the line through point A and point B. So first off, let's plot those 2 points. Okay, point A is at -2, 3. That's point A. And point B is at 3, 6. 2, 3, 4, 5, 6. Okay, so I want to find the parametric form of the line that goes through those 2 points. So let's see if we can get a line going through those 2 points. All right, let's see. We got lines at both ends. Nope. I'll select it first. All right, lines at both ends. Let's. All right, beautiful. There's our line. We're looking for that equation right there of that line. So you may be able to just pull that straight off of your graph, and that's good and well. To find your y equals, maybe your slope-intercept form, but we want to find the parametric form. So here's what we're going to do. We're going to look at the vectors for A and B, the vectors that end up at A and B. So if we call our origin O, point O, then we've got a vector OA. That is the vector 2, 3. We've got vector OB. That's the vector 3, 6 in standard form. There's vector OB. And let's say we pick some random point, any point on our line, and we call it point P. And this point P is on our line, somewhere on line AB. Then
Travis Wells, please come to the front office. Travis Wells, please come to the front office.
we find vector OP. Then vector OP is going to be whatever that point is. We'll just say that point's at XY, so it's going to be vector XY. Okay, so why do we do all that? Well, it turns out that we can use these vectors to find the parametric equation of this line here. We can use the formula that vector OP minus vector OA equals our parameter t times the difference of vector OB and OA. Okay, the proof of this equation is in 6.3 of your textbook, but this looks real similar to point slope form, and that's kind of the derivation of it. Okay, we won't spend time deriving it, but let's use it to find the equation of this line. Okay, so let's plug in what we know. We know OP is XY. We know OA is -2, 3. So this vector here is going to be x plus 2, comma y minus 3. Okay, we've got t, and our, oops, that's going to be a vector. OB minus OA. It's going to be 3 minus a -2. Let's just go ahead and, well, 3 minus -2 is 5. And 6 minus 3 is 3. Okay, we know by scalar multiplication that t times this vector is going to give us 5t. Ooh, struggle. (3t). And can't simplify much on the left side. Okay, so these two vectors are equivalent. So let's set each of their parts equal to each other. So this x plus 2 has got to be equal to the x part, or the horizontal part, of this vector. So let's take x plus 2 and set it equal to 5t. Then let's take this y minus 3 part, set it equal to the vertical part over here. So y minus 3's got to be the same as 3t. Now we can go in and solve for our x and y in each of these equations. So subtracting 2 from both sides gives us x equals 5t minus 2. Adding 3 to both sides of our y equation gives us y equals 3t plus 3. And there's our two parts of our parametric equation. So if we write them together, our parametric equation, x equals 5t minus 2, y equals 3t plus 3. And that would be the parametric form of the equation that describes this line AB. Okay, so you've got to state your vectors in center position that goes through the two given points. Random point P on our line is XY. Using this formula here, plug in what you know, simplify, set each horizontal piece equal to each other, the vertical piece equal to each other, and solve for x and y to come up with our parametric equation. Okay, one more step. Let's say we just want the line segment with endpoints A and B. So going back to our graph, what if we just want this piece of that line? Okay, we don't want the whole thing. Well, it's going to have the same equation, so we can start by using the same equation. Okay, we're going to have x equals 5t minus 2, y equals 3t plus 3. But similar to when we did piecewise functions, we're going to have to restrict some sort of one of our variables. Okay, we can't necessarily restrict our x or our y, our domain, so we're going to have to restrict our t, our parameter t. So to do that, we know that our first endpoint has an x value of -2, so let's let x equal -2. So plug it into our x equation. We get -2 equals 5t minus 2, and then solve for t. Add 2 to both sides. Divide both sides by 5. So our lower bound for our t is 0. It's got to be less than or equal to t, which has to be less than or equal to our upper bound. So if we go to our x-coordinate of our other endpoint, and you could use the y if you use the y equation, but I'm going to stick with the x. So let's let x equal 3, plug it into our equation. 3 equals 5t minus 2, solve for x. And our upper bound is t equals 1. Okay, we can write that like this, or if we go back to our interval notation. I think that's more desirable. Then we've got, let's get rid of that. Oh man, what a mess. What a mess. Then we've got our final equation. It looks like so. Right here. Beautiful. So parametric equations, being able to convert between a function equation and parametric and vice versa. Being able to come up with the graph on your calculator, excuse me, on your calculator and on paper with a table. I hope you have a wonderful day.